Hi, my name is Oliver Style. I am a passive house certifier based in Barcelona, Spain. CEO of Praxis Resilient Buildings, an engineering company working in passive house, low energy buildings in warm climates. So I'd like to share with you a presentation today called Keep Cool and Carry On, Passive House Cooling Experiences in Warm Climates. So the presentation kind of brings together lessons learned, what to do, what not to do, after about 10 to 12 years of working in trying to keep passive houses cool in warm climates, particularly warm, humid climates. And the study is focused mainly on single-family homes, but I think with lessons that have been applied to many different kinds of buildings. So where were we 2,000 years ago? Well, at least in terms of average global temperatures, we were here, what you can see at the start of the graph. And then we invented the steam engine, and then things got a little bit out of hand. And as we know, temperatures have been rising since then. So doomsday headlines abound. Record-shattering heat waves have been recorded everywhere. Warnings that we must prepare for extreme heat. Mortalities reported in heat waves in different countries, such as Canada, which traditionally is not a particularly warm climate. This graph too is quite shocking. It shows the peak mortality rate in France during the 2003 heat wave compared with the first wave of COVID in 2020. So what we can see here is that the peak mortality rate was actually higher in the heat wave in France all those years ago compared to the first wave of COVID. Obviously, the absolute numbers are much higher with COVID, but this is really quite telling. What it shows is that heat waves are indeed mortal. So we see temperatures, as we said, temperature records being broken all over the place, worryingly in places such as this, in the Arctic this past June, maximum temperature of 31 degrees, early ice breakup. Record temperatures being broken again in June in Mexicali in Mexico, 51.4 degrees, reaching 53.2 degrees in the aptly named Furnace Creek in Death Valley in the US. Coupled with that, we have, at least in Spain and I think in many European countries, a really massive increase in the price of electricity over the recent months, principally due to the increase in the cost of natural gas and its effect on combined cycle gas turbine power stations. So this is another factor really which we have to weigh in, which will be increasingly the case in the coming years. And during heat waves, obviously the stress on national grids and networks becomes more intense as active cooling, air conditioning equipment is turned on. So of course, the scale of the problem is quite daunting, but if we preach that we are completely screwed, then we probably won't gain many supporters. So we need to focus, of course, on the solutions, of which there are many, and particularly in our sector, the construction sector, there are solutions in terms of keeping buildings cool using very little energy, both with passive and active means. And that's what I want to focus on in this presentation. And I hope some of this will be useful for your work and projects. So which climates are we going to need active cooling for in the coming years? Well, we all know that for warm climates, this is the World Climate Map classification according to the Passive House Institute. We all know that climates 5, warm climates and hotter, need active cooling. The question is, are we going to need active cooling in warm temperate and even cool temperate climates? I think that will increasingly probably be the case. What we do have to do, of course, is exhaust all passive design strategies before we start considering active systems, air conditioning, refrigeration, active cooling. So this is what I want to run through first before looking at the active, various different active cooling systems. So passive cooling tip number 1, pay attention to the local climate. When you're modeling your project with PHPP, look at the climate, the official climate data, compare it if you can with data from local weather stations. Make sure that what you're modeling actually has some basis in the local climate conditions, which can obviously change quite significantly once you move in from coastal areas or move up or down in altitude. Passive cooling tip number 2, cool colors. These are traditional Mediterranean techniques, and in many warm climate cultures, painting houses white, particularly roofs, that reflects more solar radiation and stops transmission heat gain, stops the heat getting into the building so much. Passive cooling tip number 3, ground coupling. Here, what we can do is just reduce the amount of thermal insulation we put on the floor slab of buildings. Obviously, this is going to work better on low-rise residential buildings that have a significant amount of their envelope in contact with the ground. But what it means is we can use the ground as a heat sink, taking advantage of the relatively lower temperatures in the summer months, and letting a bit of heat dissipate to the ground. Of course, that's also not going to work in very warm climates in which the ground temperature is much higher. So this is also quite climate specific, but it can be a useful strategy. We also need to just be careful of minimum surface temperatures in the winter. If we don't have an underfloor heating system, we need to make sure that if we reduce that amount of insulation on the ground floor slab, we're not going to cause thermal discomfort to users during the winter months. So passive cooling tip number 4, roof insulation. Again, this is all quite logical. It's good to use important levels of thermal insulation on the roof to stop these transmission heat gains coming through in the summer months. Radiant barriers can also be useful to stop radiation heat gains and keep the house building underneath cooler. Passive cooling tip number 5, natural night ventilation and thermal inertia. So again, this is a classic bioclimatic strategy which has been used over centuries. The concept is accumulate heat in the building's mass and then ventilate at night. When you take relatively cool air into the building, that heat is removed from the building structure and then you eject it outside. So we can use the PHPP summer ventilation tool to calculate the effect of different ventilation strategies and openings. We can look at how the thermal inertia of the building also combines with natural night ventilation and how effective that is. Again, these are solutions which are going to work in climates in which the nighttime temperatures are sufficiently low. If they don't drop below 18 degrees or so at night, we're not going to have much cooling power. We're not going to be able to take much heat out of the building with natural night ventilation. So this is also quite climate specific. If we're in a coastal, warm, humid climate, of course, we open the windows at night, we're just going to bring in not only lots of heat, but lots of humidity too. So this is a very effective strategy, but it needs to be looked at in the right context and climate. So passive cooling tip number 6, ceiling fans. These are useful because they just move air over our bodies. Once there's more air movement, our bodies transpire more. It gives us a sensation of improved thermal comfort. We feel slightly cooler. It's also useful in Mediterranean homes, which are often all open in the summer. We don't shut the windows. So fans can just keep a bit of air movement going, and that can be useful. Passive cooling tip number 7, internal heat gain. So we need to make sure we're using efficient equipment and appliances so that they generate less heat and more of the electricity that they consume goes towards what they're really meant to be doing. We need to pay a special attention to domestic hot water systems, and in particular the recirculation loops in which hot water is circulating around a building, which can be a real killer in the summer. It can be a giant radiator which causes a lot of overheating, or can cause a lot of overheating problems in passive houses. So watch the hot water systems there. Passive cooling tip number 8, the most important one is opening design windows. We need to ideally avoid the temptation to over design windows that are too big. We need to really look at protecting and minimizing opening surface areas to the east and the west, which in the northern hemisphere receive more solar radiation than openings to the south, as we can see in this graph. So eastern and westerly openings, ideally we want to reduce them and make sure they're really well protected. For the winter, minimize northern openings, and to the south, make sure they're also well protected. But east and west are the most critical. We need to ideally have mobile shading devices on all openings, which can be either motorized or at least controlled with some degree of automation so that they're less susceptible to to people forgetting to drop them down. We can also use fixed shading devices to east and westerly windows. Those are best vertically orientated. Southern openings horizontal, and we can use Design PH, for example, the SketchUp plugin, as a kind of shading analysis tool to make sure that our fixed shading systems are effective at actually shading the openings. So what to watch during the design phase? If we're not going to use active cooling, then it's recommended to keep the overheating frequency, that percentage value that the PHPP verification page will show you, keep it below 5%. Okay, we know that we can get up to 10% and certify a passive house building, but really we should be below 5%, ideally below 2%. It's also good to question your assumptions about user behavior. So ask yourself, are people really going to open the windows at night? Are they going to leave them fully open? Are blinds going to be up? Are they going to be down? Is there going to be noise in the street? Is there going to be insects? You know, what's going to happen in reality, and how realistic are our assumptions? It's also recommendable to check zone by zone overheating in large and especially tall buildings in warm climates, if needed with dynamic simulation tools. And important to look at the urban heat island effect and future climate scenarios, which we can do in the PHPP with a climate tool, which takes into account those two effects. So we can stress test our design and make sure it's robust in the absence of any active cooling. So passive cooling, when will it not work? Well, there will be many situations in which the passive cooling strategies won't work. The ones I've just presented here. One example is what you can see here of a week in Barcelona during the heat wave of 2015. So what we can see is that minimum night temperatures in many of the evenings didn't drop below 24 degrees. So if you ventilate in the night, you're not going to take any heat out of the building. In fact, you're just going to heat it up more, combined with large amounts of humidity in outdoor air, which you can see in the graph on the right. So passive cooling in these kind of situations isn't going to work. And here's an even more extreme example of temperatures this last July in Furnace Creek in Death Valley in the US. Minimum temperatures of 41 degrees, maximum 54. So obviously here, if you open the windows at night, you're not going to cool anything at all. It's absolutely impossible to maintain comfort with passive cooling strategies in these kind of climates. Passive cooling does work. There are multiple examples of it. Here's a small single family home we monitored again during the 2015 heat wave, and you can see temperature and relative humidity on the comfort graph with really temperatures in the optimum comfort range, just moving outside of that. Basically, when the occupants weren't there, the red crosses when they weren't there to ventilate the home at night. So passive cooling can work. This is a climate in Barcelona, but about 900 meters above sea level in the province of Barcelona, but a little bit higher up in the mountains. So temperatures drop in the evening and passive cooling can work. So once we've exhausted all of our passive cooling strategies and we've worked out that we really need some active systems to maintain comfort, what are the alternatives? Of course, there are multiple different systems. What I wanted to present here are 6 different ones which we designed, installed, implemented, and monitored. And I've put them together in this table, which just with a quick and simple point scoring system looks at design, installation, and commissioning simplicity or complexity and cost. One being the most simple or the most economical, and then looking at efficiency, comfort, and peak load capacity. So peak load capacity is how capable are these kind of systems at dealing with extreme temperatures during heat waves. So the first 2 systems are radiant cooling systems. One is underfloor with dehumidification, and then the other is, number 2 is radiant ceiling with dehumidification. Okay, I'm going to run through each one by one, but just to summarize them. Number 3, low temperature radiators, basically floor mounted fan coils, which is both convective and radiant cooling. And number 4 is a classic passive house solution of incorporating a cooling coil on the supply air stream and just cooling using the ventilation supply air. 5 and 6 are conventional air cooling systems, 5 being fan-coils, i.e. water distribution, and 6 being splits or a refrigerant distribution. In both cases, those can be either wall-mounted or ducted fan-coil or split systems. So the technologies we're looking at here are all based on basically heat pumps involving a vapor compression circuit, which is what you can see here in the image. So number 6, a direct expansion system, basically takes heat from a room, passes it to a refrigerant through the evaporator. That goes through a compressor, which changes its phase. That means a refrigerant is able to absorb and release large amounts of heat. That heat is then taken outside to outdoor air via the condenser, and the cycle is repeated. So this is the direct expansion heat pump system. And then systems 1 to 5 include a secondary water circuit. So here we're taking heat from the room with an evaporator, passing it to water with a circulating pump that then goes through a heat exchanger. The heat is taken from water to refrigerant, and then again through the direct expansion refrigerant cycle, we're taking heat outside. So this is basically the technology, heat pump cooling technology, that we're talking about in these systems that I'm going to present now. I'm going to present monitored data which shows air temperature versus relative humidity. We're looking for data within the optimum comfort range, which you can see here, and then the PHPP calculations. When we're working with PHPP, the tool is basically trying to keep us within the range you can see here. We're looking at air temperature, not operative temperatures, which are obviously difficult and expensive to measure. And most importantly, in humid climates, we want to try and keep indoor absolute air humidity below 12 grams per kilo. Okay, so once we select active cooling in our PHPP tool, you'll see that there's that frequency of excessive humidity which can't exceed 10%. So that means that we can't have over 10% of hours in which the internal absolute humidity is greater than 12 grams per kilo. That means that 25 degrees operative temperature and 60% relative humidity is about the upper limit for comfort. Okay. This is what we can see in the high humidity index on the PHPP tool of 12 grams per kilo. So system number 1, this is a radiant underfloor cooling system where we used an underfloor system with a dehumidifier in the ventilation supply airstream. What we did here was incorporate a recirculation loop. Recirculating indoor air obviously is not a good thing to do in times of COVID, but this is what we decided to do to increase the power, the latent and sensible cooling power, by taking air from a corridor, right, incorporating another fan, an on-return valve, and then recirculating a large part of the air and allowing fresh indoor air to come in just for indoor air quality requirements. Okay, so the dehumidifier was in the ventilation supply airstream with a recirculation loop here. So that took moisture out of the air and cooled the ventilation air, and then we used an underfloor system to run water at about 17 degrees through the pipes. We can't run an underfloor cooling system in which the floor surface temperature drops below 90 degrees, basically for comfort reasons. If people are barefoot or wearing sandals, you can't drop the temperature of the floor too low. So what that means is you can't get too much heat out of the floor, about 30 watts per square meter. On the other hand, you have a lot of surface area to work with, so you can compensate the lower cooling power per meter squared by having a lot of square meterage. Obviously, it's best on tiled or ceramic floors, better to avoid parquet timber floors. We recommend, if you do use underfloor cooling, is to use low inertia systems, which have a quicker response and have less mortar, less mass above the pipe, so that they're quicker to respond. And also recommendable to use plastic manifolds to avoid condensation problems. So monitored data here from a terraced single-family home you can see during a month in July 2019. So a few hours in which the air temperature moves into the extended comfort range, but pretty good humidity below 60%, and in general good conditions. So The response from our clients in this case was basically positive. What we have found was this kind of system is very susceptible to control system issues. There need to be temperature and humidity sensors in all rooms to control condensation. There can be more maintenance problems. These are more complex systems to commission and to maintain. They're also more susceptible to people opening windows and humidity coming in warm climates. So, my conclusion is that they're not necessarily the most robust, and they're not always the best at dealing with peak heat wave conditions. So this system number 2 is a radiant ceiling. So instead of using the floor, we're using the ceiling. We're using plasterboard with 8mm water pipes running through them and insulation on top. These are located in the ceiling. We can run water temperature slightly lower than on the floor because of the comfort reasons. We don't walk on the ceiling, obviously. So we can get a little bit more heat out of a ceiling than we can out of a floor. We need to think about lighting fixtures in a design phase, and obviously users in the future, if they want to hang some new lights, they need to be careful not to drill through the pipes. Important to locate manifolds at ceiling height for commissioning to get water out of the circuits, which can otherwise be complicated. And what we did on this system was, again, as with the underfloor cooling, we incorporated a dehumidifier in the ventilation supply air stream with a recirculation loop. Here you can see some images of the recirculation loop, dehumidifier, the fan, the silencers, and on the right, images of the ventilation ducts. The ones with silver insulation are the supply air ducts, and then to the right you can see the active ceiling cooling panels, which are the ones taking where cool water is circulated. Here's data from only a very short period of 9 days for this single family home. This is a master bedroom, so not a very long time period to look at, but at least the conditions during that period were good, or within the optimum comfort range. Again, as with the underfloor system, we found that these are systems that can be complex to maintain, basically due to complexities in the control system. They're also more susceptible, of course, to windows being open, humidity coming in, and not always that good at maintaining comfort during heat wave conditions, and also systems that have a higher cost. These are not the cheapest. System number 3. So these are floor-mounted low-temperature radiators or fan-coils. So we implemented this in a single-family home in the province of Barcelona, but about 900 meters above sea level. So a warm but not especially humid climate. We can run water temperature supply at about 7 degrees on these kind of radiators. So the maximum cooling power depends on the model and length of the radiator. But to give you an example, about a radiator about 1.8 meters long will give you about 2 kilowatts of cooling power. So in this home, we located 7 different low temperature radiators, 3 on the ground floor, 4 on the first floor. Here you can see some images of the low temp radiators on the ground floor. And here you can see the monitored results of for 1 month during the summer, July 2019. So basically good dehumidification, that's kept down below 60%. Some hours in which temperatures are into the extended comfort range, but basically pretty good conditions, very positive feedback from the client, and a good solution. Again, if this was a house on the coast, we wouldn't have such good data. These are low temperature radiators which have less cooling power than what a fan coil or split system would have. So perhaps not so recommendable for very humid climates, but at least here it's worked well. System number 4, this is the classic passive house concept of using the ventilation system to heat or cool the building. So here a cooling coil is located in the supply air stream, and what we did also to provide more power, as we did with the radiant floor and ceiling systems, we incorporated a recirculation loop to increase power. Now what we found is that at least in single family homes where the heating cooling loads are fairly high or can be quite high, peak cooling loads can be quite high, the problem is basically to do with power. We can't supply water temperature too low for these kind of systems, otherwise we found that there's condensation on the casing of the cooling coil. And the cooling power is limited by basically the temperature difference and flow rate. For example, if we are in a single family home of about 180 square meters of useful floor area, and we're supplying air at 15 degrees and ambient temperature is 25 degrees, this is the cooling power that we can get. So it's 500 by the specific heat capacity of air multiplied by the temperature difference. So that's about 1.7 kilowatts. For a house of 180 square meters, that's only about 9.1 watts per square meter. So that's not really enough power, even for a passive house. This might well work. This kind of system might well work well in multi-residential buildings, which are small, compact, and where cooling loads are lower. But what we found is that at least in single-family homes, we get results like this. So a lot of hours in which we move into the extended comfort range. Really not good at all at dealing with heat wave conditions. And in our opinion, it's best just to keep ventilation for ventilation and separate the cooling system from the ventilation. A cooling coil can be useful in the spring and autumn months just to keep temperatures comfortable, but really once you get into June, July, August in warm climates, it's just not enough power from a system like this. So system number 5, we didn't have any monitored data for, so I'm just going to present system number 6 here, which is a similar technology, but here we're dealing with all refrigerant distribution. So we're just doing air to air. Heat is moved from the inside to a refrigerant and then taken outside with ducted split units, as you can see here. So with refrigerant direct expansion systems, we can get really good dehumidification because the refrigerant can be at a lower temperature than water. Can also be sometimes too low, but we can generally get good or better dehumidification with split systems than we can with fan coil and water distribution. Maximum cooling power depends on the model and size of the split unit, but for example, with a 20 centimeter high, 75 centimeter wide ducted split unit, we can get 6 kilowatts of cooling power, and that can modulate down to 1. So in a passive house, that's interesting because it means you can run these kind of units at low flow rates. That means that it's more comfortable, better, more efficient, less energy consumption, and less noise. But then you have that cooling power if you need it under heat wave conditions. You can crank it up and still maintain comfort. So here we're looking at an example of a single-family home with a ducted split unit on the ground floor. As you can see here, this was a 3.5 kilowatt system. And here we can see monitored data. So the monitored data doesn't tell all the story here, mainly because the users were out of the house when the temperatures are higher, and then they come on and turn it on. Here you can see when they've come in and turned the system on and off, not perhaps an optimal, or not at all an optimum control strategy. It would be best to run the split unit at a fixed temperature setting and low flow. But the clients are happy. They're very comfortable. Energy use is low, and under heat wave conditions, they've had absolutely no problems. So, of course, what we need to watch with active cooling systems is the global warming potential of different refrigerants. Here you can see a graph of a comparison of different refrigerants. Note the logarithmic scale on the vertical axis. So we really need to start thinking about the environmental impact of refrigerants, looking for low global warming potential refrigerants, and they're increasingly more manufacturers offering propane systems, that's R290, or methylpropane R600A, and H3 is ammonia used already on a large scale in industrial refrigeration, supermarkets, and so on, and then CO2, which of course has a global warming potential of 1. So gradually, all these other refrigerants will be phased out as the global warming potential becomes more of an issue. Something to bear in mind as well: countries which don't have legislation that's perhaps very demanding hot climates where a lot of air conditioning units are going to be installed in the next few years, this could be a real problem. So important to take into account the global warming potential of refrigerants. So conclusions, keep it simple. That's one of the main things we've learned. Also important to exhaust all passive cooling strategies before we look at active cooling systems and air conditioning. That's the beauty of passive houses is to maximize, optimize your thermal envelope, and then your HVAC systems are simpler and cheaper to design and install and use. Right? So warm and humid climates, important to use equipment that's really been made and road tested for cooling and dehumidification. Okay, that when there's a lot of moisture in the air and you're running cool fluids around the place, condensation will happen wherever it can, and so it's important to use equipment that's really up to the job. I think also good to make sure occupants are aware of the operation and limitations of their system. So when there's a building handover, whether it's a large building or a single family home, important that the occupants or the managers of the building are aware of what the limitations of their system is. Our conclusion is that it's best to leave ventilation for ventilation, separate it from cooling, dehumidification and heating. And we found that convective air recirculation systems, fan-coils or split systems are the most robust and the ones able to provide sufficient power during heat waves. And in passive houses that have low cooling loads compared to conventional houses, that means that they can run at lower flow rates, they're quieter, they're more comfortable, they're more efficient. But you have enough power to deal with peak cooling load situations. Split systems with a refrigerant distribution offer greater dehumidification power, which can be useful in humid climates. They offer a faster response. You're going air, refrigerant, air instead of air, water, refrigerant, air. And they will also have lower auxiliary electrical power consumption from pumps. The compressor is moving the refrigerant around, not a pump moving water, and so on. But important again to watch the global warming potential of refrigerants. And with direct expansion of variable refrigerant flow systems in larger buildings, it's interesting to think about heat recovery with 3-pipe systems in which instead of taking heat and dumping it to the outside air in the street, we can condense to water and preheat domestic hot water and save energy rather than heating air in the street. So thank you to all of these people who provided information and data for this study, and above all to you for your attention. It's a pleasure to be here, and I hope you have a great conference. Thank you very much.